So here we have the function f of x is equal to x over the square root of x squared minus 9. And notice inside our function that we have a square root and we also have a rational function because there's an x in our denominator. So we have a square root and a rational function kind of combined into one. So it gets a little tricky, but it's actually not too bad. We still use the same rules that I taught you earlier in this video. So when we're trying to find the domain of this function, we have to find out what restrictions we have for x, or so what is not a possible x value. And like I said before, the inside of a square root can never be negative. It has to be greater than or equal to 0. So x squared minus 9, which is the inside of the square root, has to be greater than or equal to 0. But this is also a rational function. And remember what I said about a rational function, the restrictions are that the denominator can never equal 0. And if x squared minus 9 equals 0, that certainly makes the denominator equal 0. So that cannot happen. So I'm going to erase this equal to 0 part of the inequality, because x squared minus 9 cannot equal 0, because that would make the denominator equal 0. So now I'm going to solve this quadratic inequality. X squared is a perfect square, and 9 is a perfect square, and there's a negative sign in between them. So I could factor this using the difference of squares formula. The square root of x squared is just x, and the square root of 9 is just 3. I'll put a plus sign in one of them and a negative sign in the other, and that is greater than 0. Now if we solve this inequality like a normal equation, you could probably see that you get our solutions of x equals negative 3 and x equals positive 3. So I'm going to make my number line, and I'm going to plot negative 3 and positive 3 on our number line. If you plug in negative 3 into our inequality, we get negative 3 plus 3, which is 0, times something, which is 0 on the left side. And 0 is certainly not greater than 0. So negative 3 is definitely not part of the solution, since it makes the inequality not true. I'll put an open circle around negative 3. And the same thing for positive 3. Positive 3 makes the left-hand side equal to 0. And 0 is certainly not greater than or equal to 0. So I'm putting an open circle around 3, since that makes the inequality not true. Now I'm going to pick test points for all 3 intervals. For my interval all the way to the left, I can pick any number that is less than negative 3. So I'll pick negative 5. For the middle interval, I can pick any number in between negative 3 and 3. So I'll just pick 0. And for the right interval, I can pick any number that is greater than 3. So I'll pick 5. And the first thing I'll do is I'll test my point negative 5 and plug that in for x. If I plug negative 5 in for x, I get negative 5 plus 3, which is a negative number, multiplied by negative 5 minus 3, which is also a negative number. A negative times a negative is certainly a positive, and a positive number is certainly greater than 0. So that makes the inequality true. So I can color in the entire interval where negative 5 is, because that makes the inequality true. Now I'm going to test my point 0. If I plug in 0 for x, I get 0 plus 3, which is a positive number, multiplied by 0 minus 3, which is a negative number. A positive multiplied by a negative is negative, and a negative number is certainly not greater than 0. So that makes the inequality not true. So I can't color in any of the interval where 0 is, because that makes the inequality not true. Now I'm going to test my point 5. If I plug in 5 in for x, I get 5 plus 3, which is a positive number, multiplied by 5 minus 3, which is also a positive number. A positive multiplied by a positive gives us a positive number, which is certainly greater than 0. That makes the inequality true. So I can color in the entire interval where 5 is. So now I'm going to write my domain in interval notation. The domain goes all the way from negative infinity to negative 3. I'm going to put a parentheses around negative 3 because negative 3 is not part of the solution. There's an open circle. And it also goes from 3 to positive infinity. And once again, I put a parentheses around the positive 3 because the positive 3 has an open circle. It is not part of the solution. So now I'm going to show you one more example that is kind of a trick question, I guess. Here we have the function 1 over x squared plus 16. So many of you probably can figure out by now that this is a rational function and that the denominator can never equal 0. However, let's take a look at this denominator. So here we have x squared, and whenever you square any number, it's always going to be positive. So we can assume that that squared x value is certainly going to be positive. And anytime you add 16 to a positive number, or anytime you add anything to a positive number, it's just going to make it more positive. So we can assume that this denominator is certainly positive. So in other words, every value for x that we plug in is going to give us a positive number. And if it gives us a positive number, the denominator is never going to equal 0. So there's no value for x that can actually make this denominator equal to 0. So every value for x is valid. Every value for x is part of our domain. So our answer for the domain of this function is every number from negative infinity to positive infinity. Once again, x can equal any number because it never makes the denominator equal 0. Many students try and factor this denominator and try and make it x plus 4, x minus 4, and then they say the domain x cannot equal 4 or negative 4, which is completely wrong, because this cannot be factored because there is not a negative sign in between the two perfect squares. There is a positive sign in between the two perfect squares. So this is the basic idea about finding the domain of a function. There are a few types of examples which I left out, such as a linear function, which is just a line, or a quadratic function, which is just a parabola, or maybe a absolute value function. For all those types of functions, which I just said to you, there are no restrictions for x. X can be anything. So the domain for all those functions is just negative infinity to positive infinity. So the main thing to remember is just the two rules that I taught you about square root functions and about rational functions. Remember, the inside of the square root has to be greater than or equal to 0, and also that the denominator can never equal 0. So I hope this video helped you understand the domain of a function. If you need any extra help with live tutoring or homework solutions, please feel free to visit my website at mathmeeting.com. Once again, mathmeeting.com, and I would love to help you out. Also, if you like my style of teaching and you want to see some more of my videos, please feel free to subscribe to my YouTube channel, like me on Facebook, or follow me on Twitter. That way you can see all my videos as soon as I upload them. Once again, thank you so much for watching, and take care.